Hello and welcome to this video. In this video we're going to be talking about continuity, what it is, and a few different situations and the different kinds of discontinuities that can happen. So when we talk about continuity, what that is that's a way to describe a function. And when you're thinking about the word continuity, it kind of sounds like the word continue or continuous, and that is in a sense what it means. It's asking, does this function continue in a continuous, smooth way? And so one way you might have heard about continuity back in other math classes that's a bit of an informal definition is, if we have some function, can we draw the entire function without picking our pencil up? So what I mean by that is, if we have some function, if I start my function over here, can I draw this entire function without picking my pen up once? And so in that situation, I could, right? I put my pen down and I drew the entire thing without picking it up. But if we have something, and we saw this in the limits video a little bit, if I have a function that looks something like this, stops there, and then continues like that, I had to pick my pen up right there, right? I couldn't go from this piece to this piece without picking my pen up. So that's kind of the informal definition that helps you recognize continuity, but in this video we're going to apply the more formal definition to it that has to do with calculus. So when we're talking about continuity and we're defining it in a bit more rigorous way, there are three conditions that have to be met. So if I have some function f of x and I want to know if it's continuous at some point c, we have three conditions that we have to meet. And the first one is that f of c has to exist. And what I mean by that is, if we were to go to some point c on this function, we were to plug in c for x, and then we were to look at what the y value is, that y value, f of c, would have to be defined. It would have to exist. Our second condition is that the limit as x approaches c of our function f of x also has to exist. So that means not only does our function have to be defined at this point that we're analyzing, but the limit as x approaches that value c of this function also has to exist. And then the last one, and this last one is the one that's most commonly forgotten. People forget about this one. So the last one is that the limit as x approaches c of this function must equal f of c. So what this means is that the limit as we approach some specified value of c has to be the same value as what the function is actually defined as, what the y value is at that point. And so we'll look at a few examples that might kind of help solidify these conditions. So the first one, f of c has to exist. Let's think about if we had a function that looked something like that, had that hole there, and we'll call that c. So if this was our f of x, and we were checking to see if this is continuous, we'd want to go through each of these criteria one by one, because all three of these have to be satisfied in order for a function to be continuous at a point. So if this is our function over here, let's check this first one, f of c exists. So if we look here, we have a little hole right there. So that means our function is not actually defined at c. So we would not call this function continuous, because at this point c, that first condition has not been met. So that condition is already broken. And so this right here, this kind of discontinuity, is called a removable discontinuity. So if you have a function and you have a little hole missing from it, we decided it's not continuous because that first condition wasn't met. So that means it's discontinuous, and the type of discontinuity is a removable discontinuity. So that is a removable discontinuity. So that's the kind, that's what it's called. So now let's look at another kind of discontinuity. So let's say I had a function that went up like this and was like that. So this, and we mentioned this a little bit in the last video, this is called a step discontinuity or jump discontinuity. So either of those, step / jump discontinuity. And so let's look at these three conditions and see which one of these, 1, 2, or 3, that this function, we'll call it g of x, fails. So if we look at that first condition, f of c exists. So let me call this point C. So f of c exists. Well, if we look at g of x, we have this dot filled in right at C. So that means that g of x is defined at C. We have an output, and it's going to be whatever that y value of that filled in dot is. Okay, so we passed that first condition. But what about this second one? The limit as x approaches C of our function needs to exist. And so this is a situation where that doesn't happen. That limit does not exist. So we're not satisfying that second condition. And why is that? Well, in the limit video, we talked about how if the left-hand limit and the right-hand limit are in disagreement, they don't approach the same y value, then this function has no overall limit at that spot at x equals c. The left and right hand limits have to be in agreement in order for us to say there's an overall limit. And we can see here that the left hand limit is going to be a smaller y value than the right hand limit. So there is no overall limit that exists for this function. So that second condition isn't met. So that's how we know it's not continuous. Another type of discontinuity we can have is one that looks something like this. Fill that in, call that C. And this right here is called a point discontinuity. Now you'll notice it looks a lot like the removable discontinuity we talked about, but the only difference is it has this filled in dot up here. So this is why it's called a point, not a removable discontinuity, because the function is actually defined because we have this filled in dot. So that is the subtle difference between the two. And so if we want to check these conditions, these three conditions over here for this, okay, f of c exists. So let's see, right at the x value c, we have a point that's filled in for this function. So that means our function is actually defined at C. It's going to be whatever the y value of this filled in dot is. So that checks out. The limit as x approaches C of f of x exists. Well, let's see. In order for that to exist, the left-hand limit and the right-hand limit have to be in agreement. And it looks like if we approach C from the left, we're coming up on whatever y value this is. And as we approach C from the right, we're also coming up on that same y value. So it looks like that second condition checks out. But this last one, again, the one that's most commonly forgotten, so make sure you remember it, is that the limit of the function as x approaches c has to be the same value as what the function is defined as at that point. So what that means is whatever the value for the limit is, that has to be the same as the y value that that function spits out at that point. So let's say that right on that open dot we have 4, that's a y value 4, and then right on that closed dot we have a y value 6. So using that, what I just labeled, f of c would be equal to 6. So if we plug c into this function here, then we would get out the y value 6. However, the limit as x approaches c of this function is not 6, right? Because the limit doesn't ask us what is the function defined as, it asks us what do the y values get really close to as x gets really close to c. And so the limit of this function as x approaches c is actually going to be 4. And obviously 4 is not equal to 6. So this third condition is not satisfied with this function, which is why this function is discontinuous, which is why there's a point discontinuity there. So make sure you remember that third condition. That I see students leaving that out the most, and they only check these first two. And so if you end up with a situation like this, you gotta check that third condition, because this is in fact discontinuous. The last type of discontinuity that we're gonna look at is one that, again, we've seen in some other videos. So let's say we have the function 1 over x squared right here, if you're curious. That's 1 over x squared. So, and then we think about if this is continuous. And so, first thought, you might say, well, no, this isn't continuous, because if we think about that informal definition, I have to pick my pen up from the paper to draw what's in the second quadrant and the first quadrant. And so you're right, this is discontinuous, and this is called an essential discontinuity. Essential. So whenever we have a sort of vertical asymptote here, that is called an essential discontinuity. And so we can again look at these conditions and see which one fails in this situation. So the first one, let's call right at 0, that's c. So the first one, f of c exists. Well, we can tell that since this has a vertical asymptote, the definition of a vertical asymptote is that the function is going to get really, really close to that asymptote but never touch. So this function isn't defined at c. So that first condition already fails. And then again, if one of these first two isn't satisfied, we immediately can't have this third condition be satisfied. So that is an essential discontinuity, is when we have a vertical asymptote like that. And I would recommend that you try not to get too caught up in the names of these different kinds of discontinuities. I don't think remembering the names are all too important. To be honest, I've never used this word, essential discontinuity. It's helpful to know, but more than anything, if you take away something from this video, it's being able to recognize when something is continuous and when it's not continuous. So these three conditions right here are going to be your best friends, so make sure you know those and can apply those to a variety of functions. Alright, so I hope this video was helpful. As always, let me know any comments, improvements, things you want to see in the comments below, and make sure to give it a subscribe.